earth science starting today. Yeah. And that means we're studying rocks and volcanoes and earthquakes and things like that. And today we're going to start by talking mostly about rocks. So I brought some visual aids that people can look at if they like, although I'm not going to pass them around because it makes for a mess. So let's get into it. First, we've gone through physics, we've gone through chemistry, and we learned that physics was the fundamental science and chemistry was what they call the central science. And those are because, oh look, the projector.
No class, what? Oh,
Yes, that's right. If the projector's off, there cannot be class. It's one of those rules that most people don't even know. So we've learned about chemistry and physics, and now we're going to look at earth science and see that chemistry and physics play a big role in earth science. And yes, you can actually feel free to come up and look at these rocks if you feel like in the middle of my lecture. I won't be offended.
That's what I was doing.
That's what I thought you were doing. I thought curiosity, was bring you up here. So the Earth in its entirety, 98% of the Earth's mass is made up of just 8 different elements. And there you have them. Iron is fully a third of the Earth's mass. Oxygen, almost a third. Silicon, about half of that. Magnesium, just a little bit less. And then we have smaller amounts of nickel, calcium, aluminum, or if we were British, we'd say aluminium, sodium, and other. These others are not part of the 8. Keep that in mind. Those are, that's what's left. So it's kind of surprising, we think of the broad diversity of chemicals we have in a periodic chart that has, 82 stable or 82 natural elements, I think it is. It's either 82 stable or 18 natural. I think it's natural. Anyway, but only 8 of them dominate. Question? No. Now you might ask, how do we know this? Right, this is a science class, right? It's not an indoctrination class. How do we know this?
Because we measured them.
Okay? In some way we must have measured. But as my astronomy students got to learn quite a bit over the course of the year or the semester, our measurements, we have never ever been deeper than a few kilometers below the surface of the Earth. So everything below the surface of the Earth, we haven't been there. We haven't observed it. So how can they know what's below the crust of the Earth? What they do is, number one, they take the measurements that we make from the surface of the Earth. Number two, they take our understanding of physics to make a hypothesis of what's down there. And then they make measurements to see if the predictions of that hypothesis are correct. And you might say, well, you just said that we've never been down there. How do they make a measurement? Well, the kind of measurements they can make are measurements with waves. We have sound waves, I'm speaking, and waves are traveling from me to you. We have light waves. Well, seismic waves are actually basically the same thing as sound waves. Seismic waves are the things that we feel when we have earthquakes, motion of the earth. Hey, look, Renee's running. Didn't get her exercise this morning. Everybody's looking. Good. So when there's an earthquake, we have seismic detectors all over the earth, and they measure the time that it takes the waves to get different places. And by measuring that time, they can actually determine how fast the waves were traveling through the earth. And by measuring the speed of the waves through the earth, they can then determine something about its physical properties. And so that's a measurement that they can compare against their theory. Good morning, Brittany. So it's not just complete conjecture, but at the same time, nobody has a sample in a bottle that's, we took this from the middle of the mantle. So this is a whole Earth graph. Now we're going to look at just the crust of the Earth. The crust, just like on a loaf of bread, is a very thin layer at the exterior of the earth. And so the crust of the earth, here's a cutaway picture of the earth as we understand it. You see the crust is that very thin brown layer. And then we have this reddish layer is the mantle. Inside of that, there are two pieces that are both called the core. The outer core is liquid. It's molten core. It's melted metal. And the inner core is solid. And one of the first questions you might ask is, how in the world would we know that there's a liquid and a solid core? It goes to the same two lines I just spoke about. We know that when you compress something, when you compress something, it tends to become closer to a solid state. There's one thing that you've learned that's different from that. That's water. If you take ice that's close to the freezing temperature of water and you compress it, it will actually melt. Almost everything else, if you compress it, it goes into the solid form. The reason the water melts when you do that is because it's those hydrogen bonds that make it have, in the solid phase, a bigger volume. And when you compress them, you're just breaking apart those hydrogen bonds and then it goes back to liquid. So pressure reduces or lowers the melting temperature for water. For everything else, it would raise it. So we can have solids deep in the earth because of the very high pressures. The pressure as you go down gets deeper. Why does air pressure get greater as you go down in elevation, smaller if you go up in elevation? What? Well, it has something to do with gravity. What causes the air pressure to begin with? Yeah, it's the weight of the air above us, the mass multiplied by the acceleration of gravity. So the weight of the air is what gives us air pressure. Well, once you go into the ground, the weight of the stuff above is much bigger, right? And so that means the pressure is going to increase much more rapidly. We'll have a slide here in just a moment that says, actually, no, it says the temperature increased rather than pressure. My bad. It says the temperature increases by 30 degrees Celsius per kilometer. But the pressure also increases as you go down. Because the pressure increases, the temperature it's going to take to melt stuff increases. So it turns out that this mantle, this entire mantle is near melting. So it's kind of slushy. It's near melting, but not melted. It's like the steel in the World Trade Center when it went down. You know, I just saw this on Facebook yesterday. Somebody reminding us that the melting temperature of steel is above the temperature the jet fuel burns. But it doesn't have to melt to fail. It just has to get soft. So there we have the same kind of thing. It's just kind of slushy. It doesn't flow easily. In fact, we would tend to think it's pretty solid. But it does flow. You go deeper, it gets hot enough then that you actually have the liquid. And we believe that the center portion here is mostly iron and nickel. Why mostly iron and nickel? Go ahead.
This might be a dumb question. Has anyone ever gotten to the second layer?
No one's ever gotten through the crust. They've tried very diligently to drill through the crust. The problem is it gets so hard that their metals get soft and their drills break rather than continue to drill. Of course, I haven't checked in the last year, but at that point the answer was still no, and I'm pretty certain we would have heard about it if somebody actually managed to get through the crust.
So all like the oil and everything that they're drilling for is still in the crust?
Yes.
So how deep do they estimate it is again?
Okay, the thickness of the crust depends on where you are. In the ocean, it can be as thin as 5 kilometers. If you're on a continental mass, which is what we are, the continental masses are made of less dense materials. Less dense materials float up, and so the continental masses have crusts that are in the range of around 30 kilometers thick.
It's not that.
No, it's not. Compared to the size of the Earth, it's not. You can see the numbers here. The inner core, 1,216 kilometers, that they believe is solid.
So we would probably never
never be able to drill there.
No, although in the movies they did. That's in the movies where they
How
have.
many miles is that amount of kilometers? Like, why could we never? Is it because we would die?
Because the temperature is too high, pressure is too high. So, we can't even drill through. There's no humans involved here. It's just the materials we have can't withstand those temperatures.
I'm not saying I was going to try that. Just
Yeah, you didn't have to say it. We knew. Okay, now if we look at the next section here, the outer core is 2,270 kilometers. So you put those two together, and going through the entire core, you have 3,486 kilometers going from the center to the edge of the outer core. And then you have the mantle, which is broken into lower mantle and the upper mantle. The upper mantle is marked here. The lower mantle is not. We could do some math to figure it out, but I'm not going to. This is what we believe the interior is like. And so you can see that the thickness of the crust compared to everything else is really minimal. Now, once again, how do we get this information? From seismic waves. Seismic waves, there are two kinds. There's what we call P waves. P waves are called P waves because they're pressure. So you have a pressure wave. They also are P because are P for principal. They're the faster ones. Pressure waves will go through any material, a solid or a liquid. The secondary wave, called an S wave because it comes second, it's slower. It's also called a shear wave because it's oscillating like a transverse wave. Won't go through a liquid or gas. And what they found is if you have an earthquake that occurs here, you will have this region here has no S waves. If you have a region with no S waves, they call it a shadow region. That means that there must have been a liquid that stopped the S waves. The P waves still go through. So it's pretty darn reasonable to know that there's a liquid core. A much harder question is, how do they know that there is a solid core inside the liquid core? And the answer is when the P waves get to the solid core, they send waves around the surface of the solid, and those send out secondary waves, and they measure those secondary waves to determine that there is a solid core. So there's actually good observational information to tell us what these distances are, where there's a solid, where there's a liquid, and they can calculate the speeds based on gathering enough information from different locations. Coming back to this, the mantle here is shown as one piece. That's the picture from the textbook. This one here obviously wasn't from the textbook, and it gives you more detail. The mantle has two distinct regions called the lower mantle and the upper mantle. The asthenosphere is actually this region right here, as I understand things, between the upper and lower mantles. The asthenosphere is where the temperature and pressure is high enough that the mantle material starts to flow a little. And so things that are above the asthenosphere can slide over the part of the mantle that's below the asthenosphere. And so on Earth, we have earthquakes. How many people have experienced an earthquake in their life? Good. I'm glad. Yeah. Of course, we do have a fair representation from the Golden State, where they become common.
We had one here recently.
Well,
Just aftershock.
maybe I should have clarified an earthquake that you can feel.
You can feel that.
When I was at QC, we had an earthquake that was something like 4.1. Now, those of you who have been through earthquakes know 4.1 means, well, if there was nothing going on, I might have felt something. And somebody wrote a letter to the editor in the newspaper like the next week. They were from somewhere out here in the Midwest. And they were just irate that the newspaper didn't have a huge headline. It said, I quote, "If there was ever a time for a 2-inch font headline, this was it. It was a major event." They were sad they didn't have that memento, but It's got to be 4 before you feel it. It's got to be 5 before you count it, right? Anyhow, those earthquakes occur because the earth has plates that float against each other and they rub and slide. And when they slide, that's when we have earthquakes. We'll study that more later. But the things that are sliding around each other, we call them tectonic plates. We also talked about the lithosphere as the rock sphere that's sliding. And that's the material above the asthenosphere. So it's the crust and upper mantle that are sliding around. Okay. Enough on this because, I've got a lot of slides. I was going to go super fast today. Guess not. Here's the graph of just the materials in the crust. Now, if you look at just the materials in the crust, what happened to iron? It went from being 1/3 of the entire Earth to 5% of the crust. Who could give me a reasonable explanation for why iron is believed to be 1/3 of the Earth, but only 5% of the crust? That's what? No. Did you say oxidation? No, you said, okay.
I have no idea.
With what? No. No, that is why iron is the most common of our metals. That it has to affect ground. But not why the iron is not in the crust, but yet believed to be 1/3 of the Earth. What would you tell me about the density of iron compared to, well, let's start with something easy. Iron compared to water. Iron sinks because it's more dense, right? Because we had a lab yesterday. Okay, well, the rock that we live in, the dirt and the rock that we have around, the densities of those is less than the density of iron. So what should iron do if it's in rock? If it's acting like a fluid, then the iron being more dense than the rock, it should sink. And so our theory, I'm actually not one who made this theory, right? But the scientific theory is that the iron has sunk to the center of the Earth, what we call differentiating. Differentiation is the process of separation. The more dense things sink, the less dense things float to the surface. So what we have at the surface is, in general, the least dense things that are in the Earth. So 46.6% of the elements in the crust of the Earth is oxygen, 27.7% silicon. So when we look at rocks, our rocks are very, very much composed of oxygen and silicon. Anybody know what we call oxygen and silicon? Silicates or silica. Silica is a specific formula. Silicates are things that are made of silicon, oxygen compounds, or the most common word you might know, quartz.
Oh, that stuff is everywhere.
That stuff's everywhere. What's sand?
Huh?
Primarily quartz, right? So, they talk about your computer chips made of silicon, and they say, well, you can make it from sand because it's got silicon and oxygen. So oxygen and silicon is the vast preponderance of the surface. Now our first real vocabulary word, minerals. My wife's got to take her daily complete with vitamins and minerals. Minerals are crystalline solids that occur naturally. So crystalline, what does crystalline mean? Okay, something's crystallized. Very good. Crystalline means you have an orderly and repeating arrangement of atoms. So if you have an orderly and repeating arrangement of atoms, it's a crystal. If you look at something like, this here, you can see that there's enough specific, unique shape to it that it has to be some kind of crystal. This, on the other hand, is not a crystal, you see nice smooth variation. This is a glass rather than a crystal. So crystal, you have a reproducible arrangement of the atoms. With that reproducible arrangement of the atoms, if you cut it very carefully, what we call cleave it, it will just break along a plane and you'll have a nice smooth break. So when you buy yourself, a diamond, that diamond is something that people very carefully did what we call cleave. They put a little razor blade, and they took a mallet and they tapped. If you got the razor blade in the right direction, it'll split. And I've not done this with diamond, but I've done it with other crystals for my research.
What do they do with the little pieces?
That's a good question. I imagine some of it they try to preserve to put the little pieces that go around, you ring the little stuff. Other, they probably just put it into diamond paste because diamond is very hard. We'll learn it's 10 on the Mohs hardness scale. It's the hardest substance that, elemental substance we have. And so they use it in polishing compounds and stuff because it will scratch anything. Just because it will scratch anything doesn't mean it's impervious to being broken. In graduate school, I had a friend, his father was a jeweler. Somebody came into the store and took a diamond ring and was showing somebody, see, this stuff's really hard. And they crushed the diamond. Yeah. That was an expensive demonstration. Okay, moving on. These minerals have a specific chemical composition, right? So we've learned chemical formulas. Each mineral has a specific chemical formula. And they're naturally occurring, generally inorganic. What does it mean if it's inorganic? Yeah, generally not carbon containing. Not always, but generally. So we classify minerals by their chemical composition, what elements are in it, as well as their crystal structure, the way the atoms are arranged, the geometrical arrangement. So here are some examples of crystals. Now, things we specific test are the form. When you look at something and it has, actually, I do have it here. Piece of calcite crystal, calcium carbonate. You look at this and you say, oh, I clearly can see that this has nice flat edge here, nice flat edge here. You can see some places where it didn't quite break right. If I wanted to, I could get out my razor blade and try to cleave this better and get better looking surfaces on it. So you can definitely see a crystal structure here. And when you look at this, you see that the angles on this, I'll take a hand. Don't drop it, okay? You guys can pass it around. You see that the angles are clearly not 90-degree angles. So crystals don't have to have nice square arrangements for the atoms. They just have to be very reproducible. And so you have things like trigonal and hexagonal and all different kinds of arrangements that aren't just cubic. So one thing you look for is the crystal form, the shape. Another one is the hardness. You actually test the hardness by seeing what will scratch what. Actually, the kind of test I did in graduate school is you put a certain force and you measured how much depth the indentation was. But hardness is traditionally measured by what scratches what. If I can scratch it with iron, then it's softer than iron. If I can't scratch it with iron, then it's harder than iron. And so that's how you measure the hardness. Cleavage and fracture, we'll have a slide on cleavage and fracture, but that's how it breaks. The color, clearly you can see different colors here. These are all quartz, but they look different. You have the rose quartz, it's got a pink color, milky quartz, doesn't look very special to me, and clear quartz. This one here, the rose quartz, has an impurity to give it that rosy color. These two here may be chemically identical, but they're slightly different. I said they may be. It could also, that they may be put together just a little different, or you could have something in there that's giving it the color. And then you have the density. That's what we explored yesterday, right? Separating things by their densities. And it's something that we do with other things besides just the plastics to separate them. For instance, one thing that was invented to separate apples is apples that have water cores are more dense. Apples without water cores are less dense. So you probably have noticed, you toss apple in the water, some float and some sink. You don't want to eat the ones that sink generally because they're going to be all mushy. They're water cores. But to separate them in practice, they don't want to separate them right at the density of water. So they developed a process where they put bubbles in the water to lower the density of the water. They didn't mix in alcohol like we did in lab. They put a certain amount of bubbles, and then they put the apples in, and the ones that float get packed to go to the store. The ones that sink get packed to go into apple juice.
You can just use water? Why not water?
Because they want something with a lower density than water. Why? Because that's going to separate, right? You're going to separate the densities based on the density of the fluid. And so the more water has, the higher the density. And so they want to get ones with less water than what it has if it has the same density as water. So they have to make it a less dense material. So just look at these pictures. Here's some other things just to look at. Hematite. Anybody have any idea what the hema in hematite means?
Blood.
It doesn't mean blood. Blood is called hemoglobin for this reason that this is hematite.
Red.
It's red.
Iron.
That's right.
Oh.
Hematite means iron. Fe, fair, iron. So hematite is iron-containing rock. First thing that you would notice about hematite is that it would be attracted to a magnet because iron is a magnetic metal. Another thing here is if you rub it on something, it will leave a streak. This is what's called a streak plate, and you can see on it the orange streak from rubbing an iron-containing compound on it. So that's a test to see if it has iron. This is what we like to call fool's gold, pyrite. Pyrite, I think, is beautiful in and of itself, but it's not valuable. As a child, we would go and spend a week every summer up at fish camp just outside Yosemite, and I would go and try to pan for gold in the creek there. And I would always find these things that looked like little flakes of gold. I'd excitedly go to my dad, Dad, is this gold? Is this gold? And he looks at it, nope, fool's gold. Well, how does it work to pan for gold? How many people have tried panning for gold? Like to go to Fort Sutter or something? Or Sutter's Fort, I guess. A few people. How do you do it when you're trying to pan for gold? Okay, you do it like Jocelyn. She would have done well, like in the 1920s and silent movies. Okay, you put some sand and water in your little pan that's got a reasonably flat pan, and then you sit here and you gently swirl it. And what's going to happen is if you have the swirling water is going to pick up some of the dirt and stuff. It's going to pick up the less dense dirt. Gold is very dense, so your goal there is to swirl away the less dense materials, and you're left with the more dense materials. Because gold is one of our most dense materials, you'll have a good chance of having, if there's any gold there, it at the bottom after you've gotten rid of all the less dense materials. With the grand amounts of rain that California's had this year, it's washed out a lot of rivers, bringing up the prospect that you might be able to actually find some more gold panning for gold there because it's washed away a lot of the soil that has already been panned or examined. Here's two different types of feldspars. I think it's 50% of the rock, something like that, we have are feldspars of one kind or another. One of these is potassium feldspar. The other one, plagioclase. Usually people just say plagioclase. Don't worry about saying the word feldspar. Obviously some different looks to them, but they're non-metallic looks. Here we have some that I don't actually know, so I'm going to skip over them. Calcite. That crystal that you've been passing around is calcite. Does it look like this? No, it doesn't. What's distinctly different?
The color.
The color. This one's clear. That one's not.
Gas.
Gas bubbles also. We studied enough. We know that if we put acid on the calcite, what does it do? It creates carbon dioxide gas. So it releases gas. And so that's one of the basic tests. Now this here has a reddish color. Probably it has iron in it. It's some kind of impurity that gives it that color. And finally, magnetite. Those nails are there because they put them there and they're attracted to the magnetic magnetite. It's a magnetic stone. So let's talk about this identification of stone. I think I've already talked about crystals enough, but I do want to show pictures of, for instance, diamond versus graphite. Diamond has this complicated chemical arrangement. The atoms are arranged in a very complicated fashion. You remember I was not pleased with the little square grid that our textbook had earlier said for diamond. That's a correct arrangement. It's very complicated. Graphite is made out of exactly the same atoms. It's once again, both of these are pure carbon, but they're different. Nobody gets graphite confused with diamond. You can't take your pencil lead and sell it as if it's diamond, even though it's the same elements. What's the difference in your pencil lead and the diamond? The way they're arranged. The carbon atoms in the graphite are forming rings, and those rings make so you have sheets of rings. But one sheet can easily slide against another sheet. That's why graphite is actually used as a lubricant. You grind that stuff up and you have stuff that easily slides over. And you can take graphite and you can easily separate those. This here is a picture of a diamond. This, I think it might actually be a form of coal. I just want to see you have the same carbon, looks very different. Hardness. Here is a hardness scale. You can see exactly where I got it from, the National Park Service. And so it shows the hardness numbers on the Mohs hardness scale. The hardest number, 10 for diamond. Corundum. Anybody know what corundum is? I've got pictures of it coming up. As a gemstone, we call it sapphire. Corundum, sapphire, is extremely hard. It's extremely hard and it's virtually perfectly transparent. Because it's very hard and very transparent, it's very useful in science. And so I did my master's research studying sapphire, studying pure sapphire, and studying its mechanical properties. Topaz is an 8. Quartz is your standard quartz glass. It's a 7. Orthoclase, that's a kind of feldspar, is a 6. Apatite, that's another kind of feldspar. Fluorite, it's a pretty stone. For calcite is this. This is a 3. So this is a pretty soft rock. I could easily scratch this with most anything. And then we go down gypsum and talc. Talc is very, very soft. Notice we also have some common materials. A masonry bit is 8.5. That means it's not going to be able to do much to drill sapphire or diamond. Yes.
Real diamond, and then like man-made diamond. Which one was harder?
There's a lot of debate about this, and it's driven by dollars, not common sense. When I was in graduate school, one of my buddies was doing research on what they called then diamond-like films, trying to make something that was similar to a diamond. They couldn't make man-made diamonds at that point. So it's a new technology. But since then, they've learned to make diamonds, and they can make diamonds perfect. And so part of the reason that now you have the diamond monopoly, we have a worldwide monopoly on diamonds, and they try to convince people that natural diamonds are better because that's how they make money. They have a monopoly on all the diamond mines. and they restrict the flow of diamonds so they can keep the price up. And they say, oh, a natural diamond is better than a man-made diamond because it has impurities in it. It's flawed, and those flaws are what make it beautiful. With the man-made diamond, they can make them perfect, or they can introduce defects if they want. So the man-made diamond, if it's the perfect man-made diamond, it's going to be harder because it's not going to have flaws that are points of weakness. But they can also put in impurities to give you any color of diamond you want, anything you want. So if I were to buy a diamond, which I'm not going to because as you probably picked out, kind of bitter about the worldwide monopoly and the artificial prices for diamonds, I would get a man-made diamond because they're just better. Reasonable question. Copper, you see, is relatively soft. If you're going out as a field geologist and you want to measure how hard rock is, you don't carry these minerals with you. You carry things like this. You have your knife, you have a penny, you have your fingernail, things that you can test the hardness with to help you identify what type of rock you're looking at. So that's a standard thing that geologists do, is they will try to scratch with different materials to find what the hardness is of something. Cleavage. My son was sitting next to me last night when I was working on the lecture, and I made the mistake of just Googling cleavage. And I said, no, you really need to put mineral cleavage or something like that, or crystal cleavage, because all of the pictures that came up were very inappropriate. And of course, my son's sitting next to me. I'm like, no. And he's all, oh, you better not say that word in class. But it is a standard word for what happens when we cut something in a certain way. So if I want to cleave this, like I said, I would take this, I would put a razor blade lined up with the direction of this surface. And then I give it a little tap and it splits. And it'll split nicely, right? Somebody obviously cleaved this. It didn't just naturally come to this. It'll split nicely on those cleavage planes. The cleavage planes are planes of weakness, planes where you have weaker bonds between the atoms. Based on the crystal structures, you'll have some bonds that are stronger and some that are weaker. And because it's a very reproducible structure, you have these planes that are predictable of where you have the weaker bonds, and that's where you can slice them easily. And you don't have to cut through, you just start the crack, and then the whole thing cleaves apart, breaks into pieces. So here is an example of fluorite that's been cleaved on this surface here as well as on this surface here. And you see it just formed nice, smooth surfaces. These pictures here, see the flat plane, the plane and the white plane, the yellow plane, white, yellow, and green plane. Those are showing where the cleavage planes are in those different materials. So the bottom one is calcite. That's what I passed around. And you can see it has 3 easy cleavage planes. And so you can look at that and you say, yeah, the shape of the crystal I passed around has the shape of the outlines of those different cleavage planes. Anybody know what halite is? It's a common salt. Sodium chloride. It's table salt.
Actually, salt's not.
Yeah, if you try to grow salt crystals, I mean, you can do this. You can take pure water, dissolve salt in it, and then heat it slowly. You'll have the water evaporate, and you will start to form a salt crystal as the density or the concentration gets higher. They call it an evaporite in this case because it was produced by evaporating the water away. And you can grow salt crystals of reasonable size. Okay, first of our clicker questions. Nice timing. I'm going to blow this joint up. Clicker question? Physical properties of a mineral are predominantly related to this one. Yeah.
I can do it from out here, right?
Yes, you can.
How far does this like work? I did
Anywhere you have network.
that was in my room.
It does work from your room, yes.
That'd be great.
But you know what I would do? I would not give you credit because you weren't here in class.
Plus, I'd have to constantly be on it, just waiting for it to be open, just in case. So at that point, it wouldn't be.
At that point, you might as well be here listening. Okay, we're still only half in here. We have Haley, Hannah, Jocelyn, Carmen. There's the ones who aren't present as well, so that's why it didn't sound like half. Okay, just Jocelyn and Carmen now. Jocelyn. Probably nobody recognized that tune. So we had 1, 0, 6, 7. Okay, so we had some disagreements here. We had everybody said it was either C or all of them, except for one person. So let's just look at these individually. Number 1, physical properties of mineral are predominantly related to. Since it says predominantly, it's not going to be all of the above. Right, because it could be related to all of them. Which one is the most important? So looking at the word predominantly tells me that this wasn't the intended answer. It could be dependent on all of them, but it's not predominantly. So then we have to look at these and say, well, is it the form, hardness, cleavage, fracture, and density? These are the things that we measure. Yes. This is what sets the properties. What we meant, I mean, this is good because you know what? It gives you a chance to differentiate the ideas. What creates those physical properties is the chemical composition and the arrangement of the atoms. How we measure them to differentiate one from another is by looking at the hardness, cleavage, and fracture. And what makes the difference in internal arrangements if you have the same chemical composition, that would be the external conditions. So all of these are relevant. Now, as we saw, I had a few questions on that test that turned out I shouldn't have had on the test. I try to avoid questions like this that are going to, be confusing or, almost misleading. I try to avoid those. I missed on a few on the test. I gave Stacy the list. I guess she's the only one who has the list of the questions that were bad. If you want to know which ones are bad, ask Stacy.
So, is that in your
I did already, yeah. That's why it's graded out of 45, not out of 50. Yeah. Well, there were 4 specific, and then I just added one more for good measure. Okay, so let's go to the next one. Classification. We have silicate and non-silicate. Silicate means that it's silicon and oxygen based. So silicate rocks are things, remember I said quartz is your basic silicon thing. So the rocks in here are mostly silicates. Even this here. Anybody know what this rock is? I chose it because I definitely know what it is. It's black with sharp edges. It's what? That would actually be a good call, but it's not. No, it is obsidian. Obsidian is a glass that is made out of silicates. That was black. Quartz is clear. A difference in the two is you have these other elements, aluminum, magnesium, iron, manganese, titanium, that are giving it the different colorings. So a silicate is based on silicon with 4 oxygens. So this is SiO4, 4 minus. That's the basic building block of silicate rocks. They're made out of this. Now you can take these silicates and you can bind them together. Oh, where's that picture? I didn't put the picture in. I had a nice picture of how the silicates form rocks, but apparently I didn't put it in. Among these silicates, we break it down into two general classes, ferromagnesian. Ferro means iron. I know hema meant iron too. Ferro means iron. Magnesium means it has magnesium. So ferromagnesian silicates are silicon-based rocks. Silicon SiO4 would be the base unit, with iron and magnesium. The iron and magnesium give them high densities and dark colors. And so these ferromagnesian silicates, dark with high densities. Non-ferromagnesian silicates, they're still quartz-based, but they don't have iron or magnesium. And a big piece of that family is feldspar, which is, actually, I think it was originally feldspat, S-P-A-T, that was morphed into feldspar. And feldspar just means a field rock. You go through the field and you find rocks. That's what feldspar means. And so about 50% of our rocks are feldspar. They contain aluminum, sodium, potassium, and or calcium in different amounts. You have different types of feldspars, like the plagioclase, the orthoclase, different kinds of feldspars, but they're just common rock without iron in it. So non-silicate rocks are rocks that don't have silicon dioxide or something like that. And so you can break that down to different things like carbonates. Calcite is a carbonate. Dolomite is calcium carbonate that has about half of the calciums replaced with I think it's magnesium, yeah. Or things, hematite, magnetite, iron containing. Hematite, magnetite are iron containing. Oh yeah, non-silicate means, yeah, I was thinking the wrong thing. Here are some pretty pictures. Once again, halite, sodium chloride, table salt. Spinel, magnesium aluminum oxide. Galena. I think galena is one of the really beautiful stones. My sample of galena, I'm pretty sure this here is my sample of galena. It's not so good, but you can find some really beautiful examples of galena. Pyrite, the fool's gold, is iron sulfide. Calcite, we've already seen right here. Gypsum has water as part of its formula. Question?
It's kind of random, but are there any rocks that are like poisonous for us to touch?
Poisonous to touch? Not that I'm aware of. Even if they contain arsenic, it's not going to be poisonous to touch. Don't lick it. That's true. So here's some basic classification. You have a mineral. First thing is you break it into silicates versus non-silicates. Is it silicon-based or not? If it's silicon-based, then you break it into, does it contain iron, magnesium, or not? If it contains iron, magnesium, here's some examples: biotite, hornblende, and olivine. If it doesn't, some examples: muscovite, plagioclase, orthoclase. These two are feldspars, as you can see in their names. If they're non-silicates, then you have carbonates, have carbon, oxygen, CO4. Sulfates, that's S instead of O. Oxides, again, you have oxygen something. Sulfides. You see these arrows, oxygen and sulfur. If you look back on the periodic table, oxygen's above sulfur. Anything oxygen can do, sulfur can do almost as well, but not quite. And then we have the final group here, phosphates and halides. Okay, we are out of time. Have a great